Welcome everyone to part 2 on our discussion of the naive Bayes algorithm, that is, naive Bayes for classification. What we're going to do now is move on to explore how Bayes' theorem can be extended to perform classification. And specifically, throughout this lecture, we're going to be focused on using Bayes' theorem and naive Bayes for natural language processing classification. However, we should first walk through the conversion of the Bayes theorem we just learned about in part 1 to a full machine learning model for classification. And how does this actually work? Well, the general idea is pretty simple. What we're going to end up doing is we model the probability of belonging to a class given a vector of features. So on the left-hand side, we're already familiar with this Bayes theorem. Probability of event A given that event B has occurred. And what we're going to end up doing is think about this in terms of classes and features. So really what we're asking here is, what's the probability of belonging to class C given a feature vector x, where there are k classes, that's why we have C of k, and then there are n number of features, x1, x2, x3, all the way to x of n. So all we're doing here is thinking of the idea of conditional probability of belonging to a class given a particular feature set. And what we can end up doing is using a little bit of probability math in order to rewrite this in a way that's going to be really easy for a computer to solve and come up with different scores proportional to the probability of belonging to a class. So what we end up realizing is that numerator here, probability of belonging to class C of k, multiplied by the probability of a feature set x given the probability of C of k, is equal to a joint probability model where we have probability of C of k and x of 1, x of 2, x of 3, and so on. And then what happens is the chain rule can actually rewrite this numerator as a series of products of conditional probabilities, which works perfectly for us because later on we're actually going to be able to tell the computer to calculate this product of conditional probabilities. So given that the chain rule can rewrite this, we actually need to make one final assumption in order to allow for a final conditional probability that will allow the algorithm to actually run. And this is why it's called naive Bayes. So what we're going to do is, in order to allow for this conditional probability that I'm showing here, we're going to have to assume that all x features are mutually independent of each other. So there's actually no relationship between x1 and x2, or x2 and x3, and so on. All those features are mutually independent of each other. Now, is this a realistic assumption to make? In reality, if we're thinking about a text document, this would imply that every single feature is essentially its own word. So every word ends up being a feature, and later on we'll talk about in more detail how we actually perform feature extraction from text. But you can imagine that in a document such as a movie review or a tweet or an email, that the words are probably actually dependent of each other. You don't just pick words at random, you choose words based off the other words in the document, either the word right before or the words in the next sentence, etc. So words in a document are actually definitely dependent of each other. However, in practice, this assumption that all x features are mutually independent of each other actually ends up performing okay, which is why we're going to stick with this idea that the x features are mutually independent, because when we actually run this algorithm, we end up getting some okay classification results. And so it's not a huge deal to actually treat all x features as mutually independent. But we kind of know that this idea of treating them as mutually independent is slightly incorrect or naive. And that's why we get the term naive Bayes, because it's a bit of a naive assumption to assume that all the x features are mutually independent of each other, when in reality we probably know that's not true. So, allowing for this conditional probability here, what we're able to do is create a full joint model, which is the full naive Bayes model, which is fully written as the following. The probability of belonging to class C given a particular feature set, x1, x2, and 3, and so on, is going to be proportional. So note that this symbol here denotes proportionality. And what we're going to end up doing here is having a probability of belonging to class C of k, and then that's going to be proportional and then multiplied by this series of products for a particular feature x, given the fact that you belong to a class C. So let's actually work through this in order to make it a little more clear. And I think once you actually see an example worked through in terms of documents and classifying them as positive or negative, you'll be able to quickly see how this equation is actually solved for by a computer. So what we're going to do is walk through an example of using this naive Bayes model. Now, before we actually see this example, I should note that there are many variations of the naive Bayes model, including multinomial naive Bayes, Gaussian naive Bayes, complement NB, Bernoulli NB, categorical NB, and so on. And you can check out the online documentation in scikit-learn to take advantage of the subtle differences between some of these naive Bayes models. However, for the case of natural language processing, we'll be using the multinomial naive Bayes. So since we're focusing on the multinomial naive Bayes, we should note that it's used most often in the context of natural language processing. So what we're going to end up doing is we're going to imagine that we want to create a movie review aggregation website where we need to classify movie reviews into two categories, positive or negative. And recall that since we're performing classification, this is a supervised learning task. So what ends up happening is we're using historical data. That is, using previous reviews, we can have someone manually label them in order to create a labeled data set. And this is a point where beginners often get confused when they first dive into natural language processing. They get confused with differences between supervised and unsupervised. Keep in mind, we haven't actually learned about unsupervised machine learning yet. So you should always keep in mind that for this particular series, what we're really talking about here is supervised learning, that is classification, which means you must have the known labels on historical data. Someone had to go back, read those reviews, and manually label them positive or negative in order for this whole process to work. However, if we actually have those labeled reviews and we have a model that can train and classify based off those text reviews, then in the future what we could do is just use our machine learning algorithm to automatically classify a new text review for us instead of having to hire a person to read the full review and then see if it was more similar to a positive review or a negative review. Now, how do we actually train on this text data? The way multinomial naive Bayes ends up working quite well is with a simple count vectorization model, and that is counting the frequency of each word in each document or throughout the series of documents. So what we're going to end up doing is we have a group of movie reviews, and we have 35 movie reviews in total. So we separate this out into document classes. Note here we have 25 positive reviews and 10 negative reviews. We're kind of just making up these numbers, so don't worry about them too much. But what we should note is we're going to create what are known as prior probabilities for each class. So just given the fact that I have 25 positive reviews and then 10 negative reviews, I could just convert these into probabilities just on their own. So if I kind of take a random review out of the stack of all the reviews, then the probability of belonging to the positive reviews is 25 out of 35, and the probability of having a negative review is equal to 10 out of 35. And we think about these as prior probabilities for each class. And this should feel really reminiscent of what we just discussed in Bayes' theorem. So we will be using these later, so keep that in mind. But what we're going to do is start off with count vectorization on the classes. Essentially, all we're doing is we're just going to count how many times each word shows up throughout these documents. So for instance, in the positive reviews, movie showed up 10 times, actor showed up 2 times, great showed up 8 times, and then film showed up 4 times. And in the negative reviews, movie showed up 8 times, actor showed up a lot more often, 10 times, great showed up 0 times, kind of as expected, and then film showed up 2 times. So what are the key differences that we can just glean off this information? Note here that if you have the word great in your review, it's highly likely that it's a positive review. And then maybe negative reviews tend to complain about actors a lot. So if you have the word actor, it's more likely to be a negative review. But what if you have something like movie actor or movie film? Is it going to be a positive review or a negative review? What's the probability of belonging to each class? So the next step here is to calculate conditional probabilities per class and word. And so what we mean by this is, for example, what's the probability that the word movie happens to be in a positive review? So that would mean we're just going to calculate that the word movie shows up 10 times, and there are a total of 24 instances of words in this kind of very small document set. And I know this doesn't exactly make sense with the numbers we showed earlier about number of documents, but we're keeping the calculations just simple for example purposes. But note here that the probability of having the word movie, given that it's a positive review, is 10 out of 24. Because if we know that the review is positive, then note 10 plus 2 plus 8 plus 4 is 24 words total. So what's the probability that you have the word movie if the review is positive is 10 out of 24, or 0.42. And what we're going to do is we repeat that for all the words. What's the probability of having the word actor given it's a positive review? What's the probability of having the word great given it's a positive review? And finally, what's the probability of having the word film given it's a positive review? You can see the counts here and see where the math is lining up, and then we get these probability scores. So these are conditional probabilities. We're going to do the exact same thing for the negative reviews. So what's the probability of having the word movie given it's a negative review? That word shows up 8 out of 20 times. So 8 plus 10 plus 0 plus 2 is 20. Now, something to note here is note what's happening with the word great on negative reviews. It doesn't show up at all. So the probability of having the word great given that the review is negative is 0. And we'll talk about that little detail later on in another example. But we've now calculated all the conditional probabilities for the words given their classes. Now let's imagine a new review has been created. And this is just a very simple 2-word review where the person just wrote movie, actor. Now, based on our intuition, we know that movie roughly shows up about the same in those positive reviews and those negative reviews. But what about that word actor? We can see that actor tends to show up a lot more in negative reviews than positive reviews. But how does the actual mathematics of the naive Bayes model solve for this? Well, what we end up doing is we start off with that prior probability. That is, the probability of belonging to one of the classes. So we'll start off with the positive class. What's the probability, or the prior probability, of belonging to that positive class? Recall we have 25 out of 35 reviews are positive. So we're starting off with this prior probability, and then what we're going to end up doing is multiplying it with the conditional probabilities for the remaining words in this text document that we're just kind of applying our model to. So the first word is movie, and so we're going to ask what's the probability of having the word movie given it's a positive review, and then multiply that by what's the probability of having the word actor given it's a positive review. And hopefully you can see how this connects to that idea of what's the probability of having a particular feature set given a class. That's all this is. It's that series of products that we just saw when we saw the full formalized naive Bayes model. It's what's the probability of having this particular feature given this particular class. And then what we can do is multiply those out, calculate it, and you get a score. Something to note here is that this score factor is 0.024, and the score is proportional to the probability of it being positive given the text is movie actor. So we have the score 0.024, which is proportional to the probability of the review being positive given that the review is movie actor. And we actually then repeat the exact same process with the negative class. And this is why you would repeat it for the K classes that we saw in that formalized naive Bayes formula. And again, we're going to start off with the prior probability of belonging to a negative class, which is 10 out of 25, and then the probability of having the word movie given a negative review times the probability of having the word actor given a negative review. Plug in those numbers and you get that score 0.057, which again is proportional to the probability of having a negative review given the fact that the review is movie actor. Then we compare both scores against each other. And so we have 0.057 for the negative class and 0.024 for the positive class. And what we end up doing is choosing the higher score because that higher score is proportional to the class being negative. We would assign this as a negative review, which lines up with our intuition since we saw the word actor shows up a lot more times in negative reviews than it does for those positive reviews. So again, classify based on the highest score. So this is classified as a negative review. Now we did mention an issue with those 0 word counts. So what happens with a word like great? So if we have a new review that says great movie, note here that we have the unfortunate issue that there's the count 0 associated with the word great for negative movies. Which means if you were to end up going through the math here, when you get to the portion where you have to say probability of the word great, given it's a negative review, that would end up being 0. And the main issue with this is now it doesn't matter how many times other words show up in the text. As long as one of these words has a 0 count, all of a sudden, the other text is not even going to be regarded as information, because once you have 1 0 in there, anything else you multiply it by is going to be 0. So maybe it could be saying, I had great seats, but the movie was horrible, the actors are horrible, and so on. And it could be 1,000 or millions of words of reviews just kind of decimating this movie for how bad it was. But the fact that it contained one word that was a 0 probability count, because for whatever reason, none of the negative reviews had that, all of a sudden, you're multiplying everything by 0. And you can see that this is already an issue in this very simple example where there's only a full vocabulary of 4 words for these movie reviews. So how do we actually fix this? Well, this is where we have an alpha smoothing parameter. And it's a really simple idea. All we end up doing is we just add some number of counts to all the words. So in this case, what we could do is just all across the board, add a +1 to all the words. And that way, you can make sure that even if certain words have 0, what you're going to do is just add a +1 in order to make sure that that particular probability doesn't cancel everything else out. It's still going to be really small, especially for really large documents, for large vocabularies, but you make sure that it doesn't wipe out this entire product of probabilities. So then you would recalculate the conditional probabilities and so on. Now, again, we should note how a higher alpha value will be more smoothing. So instead of just +1, you could make that +1,000, but as you add in more and more or higher alpha values, each word is going to have less distinct importance because the counts are going to be more and more similar across all the words. So you'll see in scikit-learn, the default value is just 1 for multinomial naive Bayes. Now, let's move on to focusing on feature extraction in general. And what I want you to start thinking about is, are there better ways than just simply word frequency counts to extract features from text data? For example, in these movie reviews, what if words are really common for both positive reviews and negative reviews? We would expect the word movie or film or actor to, in real life, show up about as many times in a negative review as we would a positive review. Is there a way to take into account not just something like count vectorization or word frequency counts, but also across all the documents in their classes? We'll talk about that next in the series on feature extraction from text data. I'll see you there.